In this video, we're going to be covering some challenging kinematics problems. These are intended for those with a solid understanding of the kinematics concepts and for those who want to apply their problem-solving skills to new situations. So let's get started. A falling stone takes 0.3 seconds to travel past a window 2.2 meters tall. From what height above the top of the window did the stone fall? I highly encourage you to pause this video and try this problem out on your own, using your own understanding of kinematics to solve the problem as you can. So the first thing I would do to solve this problem is to draw a diagram. So let's do that. So this is our window. This is our stone. And this is a 2.2 meter window, which it took the ball 0.3 seconds to travel past. And we can call this distance here d. And we know that there's a point H above the window at which the stone initially was dropped. So it seems like we might not have a lot of information to solve this problem. So one thing we can do is write out all of our formulas so we can get an idea of how to use the information we have. So let's write out our formulas. This is our first formula. This is our second formula. And this is our third formula. So we know that we have to use this information here to solve the problem, but one problem we have is that we don't know what the speed of the ball at this point is. It has an initial speed, but we can't assume that it's zero since we're given that the stone is dropped from rest above this window. So we can actually use one of these kinematic equations to solve for the speed of the ball at this point. So we can use this formula to solve for the speed of the ball at the top of the window. Since we can assume that the ball is dropped at rest, we can cancel out the initial velocity for 0. And then taking the square root of both sides gives us the velocity is equal to 2ad. But I'm going to replace the d with h here, because that's what we've labeled it in our diagram. Now, if you look at the other two kinematic equations, you might discover that you can actually use the distance one with the information that we now have. Where Vf can be substituted in for V naught. And so now everything in this equation is something we already know. So now we can just solve for h. So we can subtract negative 1/2 at squared from both sides. Now we can divide both sides by t, then square both sides and divide it by 2a. So I'm going to do all of those steps in one here. So this is our final expression for the height above the window at which the stone was initially dropped. And so now, if you want, you can plug it in using the information we have. And so you should get around negative 3.95 meters for your height. But you can just ignore the negative sign, so it's 3.95 meters. In this problem, it's really important that you keep all of your variables as variables without substituting in numbers at first, because we probably wouldn't have been able to solve this problem if we had plugged in all of the information we had into the variables. This formula here was crucial for our success in this problem, and that was only possible because we kept these in variables rather than trying to plug it in. So that's just a general tip when approaching these complex physics problems, is to keep things in variables and only substitute numbers at the very end. So this is the final work that we're left with for this problem. Now moving on to the next problem. A rock is dropped from a cliff and the sound of it is heard 3.4 seconds later. If the speed of sound is 340 meters per second, how high is the cliff? So again, I encourage you to pause this video and try this problem, drawing a diagram and using whatever you know to solve the problem. So again, the first thing I want to do here is draw a diagram to help us visualize this problem. So let's go ahead and do that. So this is our cliff. This is the bottom of the cliff. And at t equals 0, the ball is dropped. And at t is some time we don't know, the ball hits the ground and causes sound waves to radiate outward, which we then hear. So let's draw the sound waves. And so these sound waves are traveling back at 340 meters per second. And they are heard 3.4 seconds later. Or 3.4 seconds after the ball is dropped. So the key part to understanding this problem is that there are actually two time variables. There's the time it takes for the ball, or the rock actually, to fall from the top of the cliff to the bottom of the cliff, and then there's the time for the sound wave to travel back so that we can hear it. So we actually have to split these time variables in order for us to solve this problem. So that's why drawing a diagram can be helpful for us to visualize this problem. So let's split up the time variables. So t total is equal to the time it takes for the ball to fall and the time it takes for the sound waves to travel back so that we can hear it. So t sound. So I'm just going to abbreviate ts here. So ts is t total minus t fall. And t total we're actually given is 3.4 seconds. That's the total time for the ball to fall and for the sound waves to travel back. So we can actually just substitute 3.4 in right here. So this is our first equation that we will use later. Now you might be asking why we're trying to find the time for the sound wave to travel back up. And that's because we can use this time coupled with the speed of sound to find the height of the cliff. Using distance equals speed times time. This expresses the relationship for the sound wave, because sound waves travel at a constant rate. They do not accelerate. So that's why we can just use this simple equation as shown here. So if we can solve for Ts, and we already have the speed of sound, which is 340 meters per second, then we can find d, which is the height of the cliff, or more specifically, the distance that the sound wave travels back up. But first, we need to find the time for the ball to hit the floor. So we can use this kinematic equation here with a distance. And since we can assume that it's dropped at rest, we can cancel this out and solve for Tf. So multiplying both sides by 2, dividing by a and taking the square root, we are left with Tf is equal to 2d over a. So this is the second part of this equation that we need to know. And now we can use the sound wave to find the height of a cliff. So d, we can say, is the height of our cliff, is equal to Vs, which is the speed of sound, times Ts, which is the time it takes for the sound wave to travel back. Where Vs is equal to 340 meters per second. So now we can just plug everything in. So d is equal to Vs times Ts, which we previously found was 3.4 minus Tf, and then substituting in what we have for Tf, which is root 2d over a. So this is our final expression for the height of the cliff. Now I will say that actually solving for and isolating d on one side is kind of a lot of work. You will have to use most likely the quadratic equation, do a lot of rearranging, so I'm not going to bother through with that here. If you want, you can go on any equation solver online and have that show the steps for you. But you should get, if you plug it in right, that d is around 51.69 meters as your final answer. So this is our final work for this problem. Again, really stressing the importance of keeping things in variables, since it helps us organize our work and allows us to solve everything just at the very end. So I hope this video helped in introducing some challenging kinematics problems to you, and hopefully reinforcing your understanding of this content.